Okay. Can everyone? Oh, there we go. Okay. Evening, everyone. Thanks very much for coming through to this illustrious event this evening and that. For those of you that don't know me, my name is Nicholas Jarrett, and I'm the chairman of the Western Cape branch of Cement and Concrete South Africa. First off, I'd just like to thank our sponsors, Kalen Group, for sponsoring the talk and for also having us in this rather exceptional venue and that. This beats our normal venue locations and that. Before we get going, I thought I'll just go over the proceedings. So I'll first obviously introduce myself, and then I'll just pass it over to Tasneem Hector, who's the general manager of Kalen Group. She'll just have a few things to say, and then we'll get to the main juicy part, which is why you're all here, for Karen, the main event, to then give a discussion on LC2s, and then we'll just finish off with a little Q&A, which I'll just chair, and then a bit of networking, and then questions thereafter. So first off, I'd just like to thank our partner members who are listed here: AfriSam, Lafarge, PPC, and Sapaku Cements. CRISO, our gold members, our silver members who are listed here, and our bronze members who are listed here, 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 and here. So there's quite a lot, but there's always room for more. So if you're ever interested, don't hesitate to contact and be part of our big organization. Also acknowledging our emerging contractors who are listed here, as well as our associate members. There's also our academic members. And for those of you who are not aware, we also have an international partner with American Concrete Institutes. For those of you that are registered with EXA and that, and are a member of CCSA, you can actually claim 1 CPD point, and as well as get a discount on your EXA annual registration fees. You might have also received an email recently, but if you haven't, CCSA also now have a vacancy board where they have jobs that are being advertised, or open positions in concrete industry. If you want to find out more, you can always go onto the website, or you can follow them, CCSA, on the social media platforms which are listed here. Later this month, we have the first national conference, which is on concrete roads and structures. It's the first one by CCSA. It should be a good one, because I'm one of the speakers for this. And for those of you that don't have any of these publications, these are also available on the CCSA website, which are all listed here. We also have the Concrete Baton magazine. If any of you are interested in a good read, please chat to me afterwards. I do have a couple of copies here, so I will be happy to give them out for a good price. If you want to learn more about concrete, or you want to advance your skills in concrete technology, there is the School of Technology program which CCSA offers, which you can get on their website. And for those that are part of the in the Western Cape, we will be having a bowls function at the end of the year, which we've had for 2 years now. AfriMat tend to be dominating this, so if you want to help us take them down, then please join us for that. And with that, I'm going to hand it over to Tasneem, who's the general manager of Kalen Group and the sponsors, which I'd just like to thank again.
Good evening, dear delegates. So welcome and thank you for attending. Our special thanks goes to Nicholas Jarrett, chairperson of the CCSA, Western Cape, and his team for hosting this event at our Youngblood building, the Arts and Culture Foundation and CSI project of our group of companies. Then we would like to heartily thank Professor Dr. Karen Scrivener for being here tonight and for sharing knowledge with us. We appreciate it. So, just a bit of background of our company. So, bit of the introduction. So, Kaolin Group was formed late in 2011. Our founder's motivation was twofold. So, creating the best quality of numerous high-quality products and reducing carbon footprint. The identified product was raw kaolin, as it is readily available and sustainable. After the initial investment in an extensive kaolin mine at the west coast of South Africa, we pursued further beneficiation of our kaolin use in various industries. So this brings excitement as it will benefit our ecosystem, and on the other hand, it's cost effective. So therefore, in 2015, KG Polymer Compounds was formed to add to our developed kaolin in polymer compounds, resins, and related products. So there's just a picture of where our mine is based in Hopefield. So two adjacent kaolin deposits of approximately 500 million tons each, with an additional 4 million ton of high purity in silica sand. As you can see, our plant is very central to the Saldanha Bay Harbour, the mine, and Cape Town CBD. So that will save all on logistics. So here goes. We faced many challenges finding a way to dry separate raw kaolin. Over the years, Kaolin can now proudly say that we have successfully invented and patented a dry separation method for all raw kaolin sources. You see, the traditional method of wet separation would never have worked sustainably due to the global droughts and water shortages. So our dry separation method uses recovered waste heat from the calciner only. Isn't that amazing? So this is very important for our environment and the creation of cost effectiveness of metakaolin so that it can be commercially viable for our cement industry and low carbon concretes. Kaolin Group patented flash calcination pilot plant and method had been developed over 10 years. With this pilot plant, we have a capacity of producing 380 tons per month. And as you can see at the bottom there with the silos, so we now have a new commercial plant where we can produce 7,000 tons a month of LC2. So LC2 is a sustainable manufactured low carbon footprint, SCM, for use in concrete mortars, screeds, plasters, etc. So note that it can replace fly ash, slag, and silica fume. It is blended with metakaolin and uncalcined limestone powder. This is a great opportunity for the Western Cape especially, as it can be supplied at your doorstep. Thank you so much.
Thanks very much, Tasneem. Now on to the main event, Corin Scrivener. Who is our speaker for this technical talk. She received her bachelor's degree in material science from the University of Cambridge in 1979, and then she got her PhD from Imperial College London in 1984. She's currently the director of the Laboratory of Construction Materials in the Materials Department at the Swiss Federal Institute of Technology, Lausanne. She is a fellow of the UK Royal Academy of Engineering and has authored over 200 journal papers. Her research focuses on understanding the chemistry and microstructure of cement-based materials and improving their sustainability. In 2008, she came up with the idea of LC3 cement, and this has the potential to cut cement-related CO2 emissions by more than 400 million tons per year. With that, Karen, the floor is yours.
So, thank you very much for the introduction, Nick. So here I'm going to talk about LC3, which maybe many of you have heard of, but also LC2, and I'll explain the difference between them in a few minutes. And really to stress that these are major mitigation industry levers for the cement industry. Because in the current context, what is important is the speed and scale of reductions. This graph here shows you various climate change scenarios based on how quickly we can reduce CO2. And you basically see if we do absolutely nothing, we have a temperature rise of 7 degrees, which most people are agreed would be catastrophic. We may hardly have a human race existing at the end of the century if we go down that route. And then there's various scenarios here, and the one at the bottom is the one we talk a lot about now, because this is going to net zero by 2050. So it's no good having some wonder solution that might come along in 2070, because 2050 is this key date when we can start to turn things around and we can start to reverse this global warming. Now, at the same time, we have to realize that mortar and concrete are irreplaceable. Many people have this negative view. They say, oh, these are very high CO2 intensity materials. That's actually completely false, because as you see in the graph in the top right, the materials based on cement have just about the lowest embodied CO2 per kilogram and embodied energy per kilogram. It's only because the incredible volumes we use. We produce something like 30 billion tons of materials based on cement every year, and that's why it all adds up. And that's also why we can't use, there's a big debate about timber, to what extent it's carbon neutral. I don't want to get into that debate, because the simple truth about timber is we haven't got anywhere near enough to make any impact on this use of concrete. It's been estimated if we wanted to replace just 1/4 of concrete with timber, we would have to plant new sustainable forest 1.5 times the size of India. Now, of course, we should do that at any rate, but we still have to wait a long time for it to grow and be able to harvest it for timber. And then when you look at benchmarking on the whole building level, this is a very interesting report which was published last year. You actually see that when you put everything together and you calculate what's the CO2 per square meter of the building, in a building like this, how much CO2 for all the materials in the building compared to the square meter of usable space. And what we see very clearly here is there's not a lot of difference between what materials we use. But what there is, particularly in the concrete column, is this very large dispersion. So in this study, the building with actually the lowest CO2 per square meter was in concrete, but then also the highest. And clearly, if we can move all the high ones down to the low ones, then we're actually going to have much more impact than imagining that we can switch to wood or something like that. And the final general message I really want to stress is the incredible change in cement use. What we've seen in the last 30 years with the growth in China, you can see since about 1990, how China has grown to become more than half of world production. But in the next 30 years, that's going to change again. China's going to go down, and that's not surprising, because today they use more than 3 times as much cement per capita as the average in the rest of the world. And we're going to see these other developing regions, and at the top there, particularly Africa, where we are today, these are going to be the important regions. So if we want to have an impact on things before they happen, we have to work in these developing regions. Now, I'm going to tell you in a minute, there's no miracle solutions, but there are very good possibilities. So this is a report we wrote for the European Climate Foundation in 2017, where we really said, look, if you put the whole chain together, if you reduce the CO2 from clinker production, then you reduce the clinker in cement, which is what we're going to talk about today, and then we reduce the cement in the concrete, and then you've got to keep going, you've got to reduce the concrete in the buildings, which is often when you can save most things. We could probably reduce emissions by the order of 80%. And of course, I'm very happy to see this paper where Mark Alexander is a co-author, which emerged a few weeks ago, where they made a much more detailed calculation of all these different levers, and they came up with the possibility they could reduce 76% the CO2 emissions. So that's a great number. It means there's an awful lot we can do without, imagining these pie-in-the-sky solutions. The question is, relative costs, because all these things, like efficiency of using concrete in construction, the efficiency of concrete production, can also often save a lot of money. At the end of the day, what do you do with that remaining 20% or 24%? Well, you've got to go to something like carbon capture and storage, but that's where it becomes really challenging, because that's where the cost really goes off the scale. And while I think we're going to see carbon capture and storage sites coming online in North America, Europe, even China, I think it's going to be a lot more challenging in Africa. So we really need to maximize these things at the top before we resort to carbon capture and storage. Now, I think most people know that only a minority of CO2 emissions are coming from fuel. The major part of emissions are coming from the breakdown of calcium carbonate. And, as I've said repeatedly, there's no silver bullet. We can't really make clinker in a different way because of the resources available on Earth. We don't get hydraulic materials. And, there's a lot of media hype about this, but if you really analyze it, the solutions are impractical, costly, unscalable, or will take way too long to mature. So, if you want me to go into detail of anything you've heard about, I'm very happy to do that, but believe me, they are not going to work. But what does work is this use of blended cements. So that's substituting part of the Portland-based clinker with other materials. And this has been around quite a while. We've been using for several decades these substitute materials like fly ash, like slag, like fine limestone, and now calcined clays. And that's why calcined clays are interesting, because if we look at the availability of these traditional SCMs, we see the amount of slag and fly ash available worldwide today is only about 15% of the cement production. Now, of course, I know that varies locally. I know in Johannesburg they've got lots and lots of mounds of fly ash, but in other parts of the world, and even down here on the Cape, you've basically got to ship this fly ash all the way down here. And slag, it's an even worse situation, because worldwide we have about 8% of slag compared to the cement demand, and nearly all that slag's used. So if you say, well, I've got to have high slag in my project, you just take it away from another project, and the net result is no further reduction in CO2. So where else can we go? And this is where calcined clay comes in, because it's really the only thing that's available in the enormous quantities we really need to make a difference. And this led us to what we call the LC3 project, where we realized not only were these calcined clays, these clays that you can calcine were massively abundant, but we could get a synergistic reaction with limestone. Limestone's also super abundant, often at the cement plant, and we could then go to very high levels of substitution. So what is LC3? So LC3 is this family of materials. We've developed it with a landscape of partners in Switzerland, India, now Kenya. And basically what we do is we take about half the clinker, but we can even substitute larger amounts now, And we replace half of that CO2 emitting clinker with this combination of calcined clay and limestone and gypsum. And I'm going to come back to the gypsum later because that's a quite important point. And then with this combination, which we call LC350, you can see we can get comparable strength to the reference Portland cement, and we can start to get that strength as early as 7 days, and even at 3 days, even at 1 day, the strength is nearly the same as the reference. Now, I said I'm going to come back to the sulfate, because you do have to adjust your sulfate. If you look at this calorimetry curve here, what we've got, first of all, is the peak that's the reaction of the calcium silicate, the C3S, and then superimposed on that is the reactions of the aluminate phase. Now, a lot of people think you need more gypsum with calcined clay because you've got more alumina in it, but that's actually incorrect. It's really more to do with the surface area of the addition you make. The surface area speeds up the reaction of the C3S, and during that initial reaction we get sulfate absorbed on the CSH, and then that sulfate's later released. So the faster you're reacting your C3S, the more sulfate is absorbed, and you have to compensate for that. And there's some very detailed publications that came out in the last few years that can explain that in detail. But you can adjust this quite easily by looking at this development of heat rate. And what you need to have that sort of pointed alumina peak occurring after the silicate peak. Now, here I'm coming back to LC2 because, so far I've been talking about LC3, and LC3 is what happens when you mix all these ingredients together at the cement plant and you just use that as the binder to make concrete. Now, in several parts of the world, North America, UK, South Africa are the notable ones, the practice has been not to have blended cements where everything's blended together at the cement plant, but to add the additions like slag or fly ash at the concrete level. And you can do that. It's really exactly the same because at the end of the day, you end up with the same mixture in the concrete. And that's what we call LC2. So LC2 stands for limestone calcined clay, and the bit of gypsum, as I just explained, and this is what Kaolin Group are now producing here in South Africa. And that's just another way of showing the same information. Either you put everything together in the same bag, or you have one bag of OPC and you have another bag of the calcined clay with the gypsum and the limestone. Now, the essential point is, why can we get such high levels of replacement? And it's all to do with the presence of kaolin. So kaolin has this atomistic structure, which I've drawn here, where we have one layer of alumina, one layer of silica. The silica can react in the classic pozzolanic reaction, but the alumina also reacts with the limestone, and this is where you get this synergetic reaction, producing those peaks I've circled in red, which are mono and hemicarboaluminate. They're already present in limestone cement, so they're not something new. We know exactly how they behave, but we produce more of them in LC2 or an LC3 mix. And this is the very important comparison, because here we're comparing the mixtures made either with calcined clay, or with fly ash, or with slag. And if you look at the long ages, 180 days, you see all the strengths are pretty much the same. But what's particularly interesting about the calcined clay mixtures is they catch up the strength much, much earlier. So in this example where we've mixed everything together in the laboratory, it catches up at 4 days, but in some situations you can catch up earlier at 1 or 2 days. And you can look at the reactivity of these different SCMs. We spent a lot of time developing this, what's now a standard ASTM C1897, where we can compare the different reactivity of different SCMs. And you can see the clays, which are in orange here, are very comparable with slag and with silica fume, but of course the amount of silica fume we've got available is really minuscule. And these three, slag, calcined clay, and silica fume, are much, much more reactive than fly ash or natural pozzolans. And the fact they're more reactive will mean you can go to higher levels of substitution, and higher levels of substitution means you can save more CO2. And why does this save CO2? Well, here's a detailed analysis of the energetics for producing calcined clay. These are figures taken from a real project. They're going to be slightly different in all the different projects, but here in this version you see that you've got emissions that are 4 times less than clinker. So for every bit of clinker you take out of your cement or your concrete, you've got 4 times less emission, and then you've also got the limestone on top, which has got effectively 0 emissions. So the potential question is, what kind of clay is suitable? Of course we need this mineral kaolin, which, as I've already explained, but we don't need high purity kaolin. Of course, high purity kaolin is used for things like treating papers and ceramics, things like that. We're not competing with that. We're looking at reserves with a fairly low content of kaolin, which are not in competition with these other uses. And we're certainly not talking about agricultural soil. That's the very last thing you want to use. This is an industrial operation. You need a quarry, you need to extract the material professionally. And we've now studied well over 100 clays from all around the world. You can easily measure the kaolin content by looking at the loss on admission, and we see that this kaolin content correlates pretty well with the strength correlates pretty well with the kaolin content. In fact, if you look at the top curve for 90 days, you see that in fact it's not completely linear. It kind of plateaus out above about 60%. So you get very little extra benefit for going above 60% kaolin. And those red lines are the strength of the reference plain Portland cement. So you can see at 20 days you only need roughly 30 to 40% kaolin to match your strength of your reference Portland cement. So the ideal kaolin content is in this range 30 to 60. If you have higher contents, you can blend in more limestone, which gives you even more savings. If you have lower contents, you can enrich it by separation. And we know Kaolin Group had developed their own separation route, but just to give you another perspective, these are a couple of slides I got from Losha, who are doing the separation with the vertical roller mill. And they start with this mixture of calcined clay and quartz, and then they can really separate this with a high degree of efficiency. Here in the calcined clay, they end up with about a clay purity of 83%, and the quartz has a purity of about 94%. So, you have different methods which are suitable for different clay deposits, and it's clear that what the Kaolin Group are doing here gives a similar outcome. Now, the world distribution of calcined clays is very abundant. Everywhere you see this orangey color, we will have calcined clays. You can see South Africa's maybe not as good as some parts of Africa, but you can see these very good deposits right on the coast on the Western Cape. And there should be ones also on the eastern, but we haven't heard so much about those. The clay you calcine with existing technology, you want to be in this temperature window 700 to 850, and you can do this either with rotary kiln or with flash calcination. There's not really much difference in the reactivity you produce. The rotary kiln tends to be more robust. You can deal with higher moisture contents. This shows one of the first plants, which was set up by Argos in Colombia. This is another greenfield plant which was built by Simpor in Ivory Coast. And what was particularly interesting in this particular plant is that they could demonstrate it's possible to control the color. So many of you know that cements tend to be reddish, and some people say, well, we don't want red cement. Well, if you don't want red cement, you can make it grey, which is good news. But now actually it seems more companies are coming around to the idea that it might actually be a good idea to stick with the red colour. And other clays to have much lower colour, particularly this one coming from Kaolin Group. And we started with these fairly basic structures we built in India, but now Argos are really building at a full civil engineering scale, as you see here, and being able to use this product in exactly the same way as they can do existing cements. So what are the key advantages? Well, the absolute key advantages are resisting chloride ingress and suppressing alkali silica reaction. And those are, of course, the two durability issues you really have here in this part of South Africa. This table here shows the chloride resistance, where we just simply put the cube in a solution of chlorine. The black curve is the reference Portland cement. The red ones are the blends with slag, which you see improve the situation. The blue ones are the blends with fly ash, which improve it again, but the best of all are the purple ones, and the purple ones are the ones which contain this blend of calcined clay limestone. So you get better resistance to chloride penetration than you do with fly ash, and better early strength, and very good resistance to alkali silica reaction. These were some studies we did with the Thai group, SCG, and you can see even if you add in extra alkalis, they were producing a low alkali cement, which is actually quite wasteful in terms of CO2. But even if we increase the alkali content quite substantially, we still get absolutely no reaction in alkali silica. Some of the problems people talk about, well, they talk about difficulty with workability because you've got a fine material, and they talk about carbon. In terms of workability, the really important point is we have superplasticizers that can deal with this. And on the counterpart, we have very good cohesion with these blends. So they're very suitable for self-compacting concrete. This compares the admixture demand for a self-compacting concrete with fly ash and one with LC2, and you can actually see the LC2 one has a lower demand for water-reducing admixture. And this was one of the first projects we did in India. You can see that the mixing the concrete is not at all technical. It's just done by volume batching by those people there and in a sort of small mixer. And nevertheless, they could batch after batch obtain this very good cohesive concrete with no bleeding, no separation. In terms of carbonation, well, there's no such thing as a free lunch. The whole point we've been trying to work on is reduce the amount of limestone, which is giving off CO2 in the first place. And that inevitably means there's less capacity to absorb CO2 afterwards. So low carbon materials will carbonate faster because they contain less buffer. But the important thing is that what happens with LC2, LC3, is really exactly the same you have in fly ash. This was one of the first projects we did in India. We built these little columns. One column is a fly ash blend, typically used in India. Fly ash at about 25 to 30%. And the other column is an LC350 blend with now 50% level of substitution. And then if you look at the carbonation rates, you can see really systematically the carbonation depths in the LC3 mixtures are lower than the fly ash. And fly ash has already been used for decades in India, so we know well how to control the carbonation. Of course, much concrete used in interior situations is never going to be, it's going to carbonate, but it's not going to have a reinforcement corrosion problem because it's much too dry. So whether carbonation leads to corrosion of reinforcement is very much a question of moisture content. And it's only where you have this alternance between very wet and very dry conditions you might, and I stress might, have a problem. So, maybe a few balconies, but, you can make your balcony in a different mix. Why waste all that CO2 in the whole rest of the building? And now we've studied engineering properties, and we see that these all correlate with compressive strength in exactly the same way. So here's the bond strength for reinforcement, here's the flexural strength, here's the split tensile strength. You see that all the points are on the same line with OPC and the fly ash blends. Elastic modulus, same thing. Shrinkage, all very much of a muchness. The only thing that seems to be different is the creep. And we seem to have a lot lower creep with the LC3 than we do with the other blends. And we're actually looking into this further because my colleague, who's a structural engineer designing high-rise buildings, thinks you might be able to make major savings in these kind of buildings because of the lower creep. And, you know, just to show that LC3 concrete can be used in all kinds of applications, this is a small study we did where we compared LC3 concrete with the concretes prescribed in Dubai. So in Dubai, because they have a lot of durability issues, they're prescribing concretes containing fairly high amounts of slag and silica fume. This then shows what happens when you take out the binder they put in and you substitute it with LC3. Well, you can actually see that 2 out of these 3 concretes, the 35 MPa and the 50 MPa, are actually massively over-designed. They have much higher strength than needed, while the C90 concrete is under-designed. So then we kind of looked at these mixtures again. We always did the life cycle analysis, and we saw what we could do by taking out some of the cement content, playing a little bit with the water-cement ratio, and now we can come up with mixtures. I don't know how that one got there. That's the chloride mixtures, which you can see that the chloride penetration by this RCPT method is always lower in the LC3, but what's more important here is the compressive strength and the global warming footprint. So we're now hitting the compressive strengths we need, and in the case of the reference concrete to the LC3 optimized, we can save 25% for the basic concrete, we can save 21% CO2 for the kind of intermediate concrete, and we can still save 10% of CO2 for the high-strength concrete. And remember, the high-strength concrete they prescribed wasn't actually even meeting the criteria. So if we put all this together, using calcined clay has a huge potential for lowering CO2 emissions worldwide. This is a simple calculation we made, taking the level of substitution today around the world and saying if we then went to a technically quite easy substitution level of about 40%, we could save another 400 million tons of CO2. And if we think of a perspective on 2050, we can probably do twice as well as that with a bit more effort. And we can save money. So this is the comparative cost of LC3 mixtures compared to an OPC reference. There's a detailed report on that on our website. And in fact, since we calculated these figures a few years ago, the balance in favor of LC3 has really been tipped further because energy prices have gone up, because most of the price of cementitious material is related to the energy you use. Because we've got a lot less energy, we can save on an integrated plant where you're also producing clinker. We can also save in a grinding plant. And lastly, I just put a few slides. I'm going to go through these quite fast, but Robin De Beer has a copy of these if you want to know more. And this is, you know, how we can deal with this in standards based on the UK situation, which closely mirrors what happens in South Africa. And making LC3 is now not a problem because that is in the EN 197 standard. When you come to LC2, it's a little bit more complicated. You either can make this LC2 blend or you can make the blend of metakaolin on its own. Each of them has different criteria according to today's standard. If you add them all separately, this is covered by the present British standards. If you want to start adding them together, then it's a little bit more complicated, but there are proposals to the British Standards Authority to deal with this, and they've agreed to correct this, and then options for LC2. Now, why is LC2 so interesting? Well, it's particularly interesting in that it's very flexible. So you can increase or decrease the amount of addition you have depending on your application, and it also has a very long shelf life. So you don't have the problem of a clinker-based product that kind of tends to go off in about 6 months, but we've actually stored LC2 for 4 years and more, and the reactivity needs to stay very constant. And there are proposals for how you can deal with that. I'm not going to go through them in detail, but you know, as I say, Robin has the slides and he can discuss those more with anybody. So I think I've gone on well long enough. I don't want to bore you to death. I think the main message is that we can make these substantial reductions in CO2 just by applying known technology and working really through the value chain. So we can make reductions at the cement level by increasing the use of SEMs, either at the cement level or when we make the cold concrete. We can also make these reductions at the structural level, which is often forgotten about. And this involves the different parts of the industry working together. And all of these will actually lower costs. We won't be able to get completely to zero in this way. We'll have to have some measure of carbon capture and storage, but this is where the price completely changes. And so we really want to maximize everything at the top before we have to resort to carbon capture and storage. And calcined clays then have this incredible role to play here because they're so widely available, and the technology is all available now and really at basically any scale you like. And to try and stimulate the industry to work better at a global level, we formed this, which is called the Globe Consensus, to try and encourage measures like, for example, this benchmarking of CO2 in buildings. And you can find more about this on the web or ask me about it. So for those who are students in the audience, you might like to attend our doctoral school, which is looking very much at analytical methods, which takes place next February. For those of you who want to know the latest in terms of calcined clay technology, the 4th International Conference on Calcined Clays for Sustainable Concrete will take place in May next year in Nanjing, and I've got some flyers on that if anybody wants some. And with that, I'd like to thank you for your attention and hope to answer any questions you may have.
Thanks very much, Karen. That was a very informative presentation, a lot of information to take in. We'll take some questions now. Any questions in the audience? Yes.
My name is Mark from Concrete Testing Services, and I'm not a cement chemist, but a concrete technologist. You speak about gypsum. So there's 5% additional gypsum in your...
It's not 5% addition. The overall content in the mix is at 5%. So you take out half the cement, you take out some of the gypsum, you've got to put some of that gypsum back in. So typically in LC2 you may have 2% addition, but you really want to check that by the calorimetry.
And obviously setting times come to mind, so it's just, is it something to watch? Or I see you smiling, so you must have had
No,
good
setting
questions.
times have very little to do with gypsum addition. This is a very old anachronism. You know, basically the amount of gypsum you need to add to control setting time is very, very small compared to the gypsum that's added today. And the gypsum that's added today is based on optimization of like 1 day or 28-day strength. So forget about setting times. That's nothing to do with gypsum additions. What is important is to make sure you have your illuminate peak coming after your silicate peak. Because if it doesn't come after, then you will impair the reaction of the C3S. And that's the major phase that's there that's giving you most of the strength. So that's why you need to adjust the gypsum. And you can do that by this isothermal calorimetry. I saw the figures you had coming from WITS, except they'd squashed everything up on such a small scale, I couldn't really see what was happening in the first 24 hours, which is where you're really interested.
Thank you. My name is Mark from the University of Cape Town.
Yes, I did know that.
Karen, thank you very much. Just a few points. Just to mention that we recently completed a major study looking at 4 African clays and LC3, the 2 of them, the one from Western Cape, one from the Bronkhorstspruit area, and 2 from Tanzania. And that information is available. In fact, it's in the open domain for anybody who wants to look at it. Number 2, this question of standards. This is always going to be an issue because it's not simply the standard of the material, but it's the standards that have to find their way right through the whole suite of construction standards, which means that our specifying authorities have got to sort of cascade it down through the various levels. And Brian on my right will tell you that that's never an easy job. That's not to hold it back. I'm just mentioning that it's a real issue. Number 3, only 20% of our cement goes into high-grade reinforced concrete and pre-stressed. The vast majority goes into lower-grade applications, blocks, bricks, mortars, renders. Can you comment on that in terms of this technology? Thank you.
Yes. So taking those in order, of course, I know very well about the thesis of Emmanuel Leo because I was external examiner on that, and that's a very nice piece of work that really documents the durability parameters of these different clays throughout Africa, and shows a very good performance of this one from the Hopefield side. Standards, yes, this is really where we have to work in more detail, and it's very, very different from country to country. I have to say, I think, UK, South Africa, and North America kind of shoot themselves in the foot by this addition at the concrete level, because it tends to be more simple if you mix everything together at the concrete level, but that's what it is, and the sponsors of this event are trying to capitalize on this fact that people want to add it at the concrete level. And then, there's 2 aspects, the aspect of durability and the aspect of how low you can go in CO2 emissions. And I showed that graph, which is about the reactivity of these different additions. If you have a higher reactivity, this means you can go to higher levels of substitution. So we compared in detail with a natural pozzolan that's been added in Chile. And there they have a kind of general use concrete which has 60% clinker and 40% natural pozzolan. We could actually match the performance of that by going down to a clinker content of only 25%. Okay, that's going to cause you even more problems than standards, I know that, but it really illustrates how, when you're thinking about CO2 reduction, the more reactive a material you have, the higher the level of substitution and the more CO2 you can save. So I hope that gives you some of the answers. I'm very aware there's still a lot of work to be done on standards, but, if there wasn't any work to be done, we could all shut up shop and go home.
But it also opens the door to performance-based approaches.
Yes, and I'm now heading a committee in Ryland, which is starting with performance standards on the cement level. But I think we need to go to more performance standards and simpler performance standards. There's this very, very complicated one coming for concrete in EN 206, but we need to really think about more simple approaches.
Brian Perry from Cement and Concrete, and also chair of the relevant SABS committee that looks after all the standards that we're talking about. We fortunately adopted the European Standard 197-5 earlier this year. Unfortunately, in South Africa, cement is a compulsory standard, and until it goes through the government gazette from the national regulator, it can't be used. So there's a problem with that. Secondly, none of our specifications allow the addition of anything other than slag or fly ash or silica fume as extenders at the batch plant, so that we'll have to get that changed. Have the Europeans done anything on developing a standard for an LC2 extender, or would it have to be putting the L and the C separately?
Well, that's what I showed you at the end very quickly, and I know you couldn't absorb it all, but you can look at the slides afterwards. And those were developed with my colleague Fernando Martorena, who's been working a lot in the UK, and in the UK they think they now have a solution to this. Of course, it's very good you've adopted EN 1975. I know about this problem of publication because we spent years and years changing the standard in India, and then we had to wait, I think it was something ridiculous like 18 months for them just to publish it in the official gazette. It's kind of ridiculous that things have been slowed down by these trivialities. So I know very much about these things. And I mean, I know that there are obstacles, but I think where there are obstacles, we just got to work on overcoming them, because this is the future. And, you may have lots of fly ash now, but the pressure is on all countries to get out of coal. Even India has said they're going to get out of coal by 2060. I hope South Africa's not going to be far behind. And then, eventually the fly ash is going to disappear. At any rate, as I've said several times, fly ash is not a high-performance additive compared to slag and calcined clay.
Just a final comment, 18 months, you're very lucky.
Yeah, I know. It was crazy, but I mean, basically we had someone phoning them up every week in that 18 months to push. It's crazy.
Okay, we have a question here.
Thanks, Karen, for your presentation. I'm John Babafemi from Stellenbosch University. I just want to ask, with LC3, from what you showed us is SEM1 that was used to combine, that you combined with LC2. I know PPC in South Africa, they do not produce SEM1 anymore, but they have SEM2 that has about 6 to 20% of limestone. So what would you advise in combining LC2 to SEM2 with about 6 to 20% limestone?
Well, we were looking at that yesterday. I think they do produce still some SEM1, and they produce this SEM2 with limestone. Now, I mean, you just have to look at what application you want. If it's, not a very high performance application, I think you can still add LC2 in the proportions we're talking about, which is roughly 2 to 1 metakaolin to limestone. If it's a more high performance application, you may want to cut down the amount of limestone and just add the metakaolin. And what's interesting about the kaolin group plant, which I saw yesterday out in Atlantis, is they've got, basically 3 silos with the gypsum, with the calcined clay, and with the limestone. So they can actually make any blend, almost on demand if they want to, and adjust according to what cement. But yes, I mean, this is a big issue in the US as well.
Question there.
Could you please comment on fire safety and the impact of fire?
Well, I'm not an expert on fire, but the compounds you've got in this material are exactly the same as you've got in an OPC. So we don't expect the fire performance to really be any different. We have got a study going on that in India, but I don't have the results yet. Jackie was showing me this incredible product he's made, which is really showing excellent fire performance. You can have it kind of really hot on one side, and it's really cool on the other. So we can get good fire performance. It's a question of making the right formulation. But essentially, you're not looking at anything that's any different from what's already out there. The products you're forming are the same as you have in fly ash cements or slag cements. So it's the same thing.
Sorry, just maybe one more question. Has there been any research on the response of LC2 or LC3 with the different types of admixtures available?
Yes, we've done a lot of work on that. So the good news is that LC2, LC3 work perfectly well with all the admixtures that are on the market. It's not like one of these geopolymer systems where none of the existing admixtures work. And all the admixture companies have now developed specially adapted admixtures that do even better. So Sika, Criso, all of these companies have their special admixtures for calcined clay. We've tested a lot of these. They do an excellent job. And depending on your system and your formulation, the extra demand for plasticizer can be from nothing, can be exactly the same as the Portland cement, to maybe double, but it depends on a lot of different factors, so you can't give one figure.
Any other questions? Okay. Right, great.
Okay.
Well, thanks very much for that, Karen.
Thank
much
you.
appreciated. Before we close, I just want to highlight for those that are wanting CPD points in that, don't forget to sign the register and that if you want to claim that. Also, someone that's RSVP'd highlighted they would like a kosher meal. If you are here, you can pick it up at the bar there. Otherwise, thanks very much to Kayla and the group again for having us, and most of all, thank you very much to Karen for coming all the way through. Okay, thank you.